Dear student, welcome back to the series of discussion on compressible flow. Today we are going to discuss what the solution of another numerical. So the numerical is showing on your screen. It says that convergent divergent nozzle receives steam at 5 bar and 200 degrees centigrade, expands asymptotically into a space at 2 bar. Neglecting the inlet velocity, calculate the exit area required for a mass flow rate of 0.3 kg per second in the following cases. You need to consider first when the flow is in equilibrium throughout. Thereafter, when the flow is supersaturated with PV to the power 1.3 is equal to constant. And for these supersaturated cases, you need to determine the supercooling and degree of supersaturation. So let's first of all discuss the first part. The convergent divergent nozzle is given. So we can have on the HS diagram or Mollier diagram, you can locate the state 0 by locating the corresponding pressure of 5 bar and temperature 200 degrees centigrade. And in the first cases, since the flow is isentropic, so it will there will be the one vertical line passing through 0. So at the 2 bar, if in the vertical line will cut, then that will represent the the inlet exit conditions. So from a steam table we can have the data corresponding to overstate. So from the steam table or Mollier diagram you can read it out. The V naught will say, so from steam table or Mollier diagram we can read it out for the specific volume, enthalpy and entropy. Also the S1 is representing the as the entropy at the exit. So since the 0 to 1 is asymptotic process, because every intermediate state is given as a equilibrium, so it will have the asymptotic process. So that can be written as a S1 is equal to S naught, and S1 can be written as a S1F plus X SFG. So from the steam table we can read it out the data for S4SF and SFG, and that S1 can be equated as 7.059. Then we can get a value of X1 as 0.972. Therefore we can determine the H1 value. So H1 we can determine HF plus X HFG. So from all the data we can read that out from the steam table and substitute, then we will get a value of 2645 kilojoule per kg. And similarly in the V1 cases also we can determine VF plus XFS X VFG. However, it can be observed that VF is very small and that can be neglected. So here it is neglected. So directly it has taken the X into VFG. So that we got the value 0.86 meter cube per kg. Therefore, we got the H1 value from, and we have the H0 value. So with this enthalpy drop, we can have the velocity V1 at the exit by this expression corresponding to the enthalpy drop of H0 minus H1. So let us substitute H0 and H1 value, then we will get H1 value, V1 value as 648.67 meter per second. Therefore, we have the mass flow rate is given as a 0.3 meter per second. We have at the exit the specific volume we have calculated, volume velocity we have calculated from the continuity equation. The mass flow rate is equal to rho AV or AV upon specific volume. So from this equation we can calculate area h omega s is given, mass flow rate is given, v1 we have calculated, specific volume we have calculated. So area can be calculated, and it is calculated. It has evaluated as 0.000398 meter square. So the required area will be 398 mm square. So this is our the final answer, or the required answer that need to determine when the flow where the equilibrium throughout or isentropic. Now the next, the flow is assumed to be supersaturation. So in that cases, let us have a derive what will be the expression for the exit velocity. In that cases, let us have the property diagram. First of all, property diagram, property relation dh is equal to tds plus vdp. So if it is the isentropic flow, that means ds will remain same. So dh will become vdp. Also for the stagnation flow, we are knowing that h naught will be the h plus v naught square. So here h naught is remains constant and h is varying, v is varying. So we can differentiate it, then we will get dh minus vdp. Here we have the dh is equal to vdp, and here we got vdp. So by using these two relations, we got a relationship between pressure and volume. So pressure, volume, and in terms of velocity. So we can have a relation of pressure and volume for isentropic flow as the PV 1.3 is equal to P1 V1 1.3. So this is because the supersaturation flow follows PV to the power 1.3 relationship. So we can replace, in a state of volume, in terms of pressure, we can replace it as a constant upon P to the power 1 upon N. Here N value is 1.3. And if we can integrate the velocity, that is the in the inlet velocity is v naught, and outlet velocity in the case of supersaturation, say it is vr. So we can integrate velocity from v naught to vr, then the corresponding pressure will vary. At the inlet it is p naught, and at the outlet it is pressure v1. So by integrating, we will get an expression like this one. Also, it is mentioned that neglect the velocity at the inlet. So at the inlet, we can neglect the velocity. At the inlet, we can neglect the velocity. By then, in this expression, we will substitute value v naught is equal to 0. Then we will get an expression for the velocity at the exit of supersaturation flow, at the exit of nozzle for the supersaturation flow, as Vr square upon 2 n upon n minus 1 p naught v naught minus p1 Vr. So here you should give attention. This is the specific volume at the exit state corresponding to the supersaturation. So this can be determined using the relationship P pressure volume, that is given PV to the power 1.3. So in that cases, it is VR upon V naught by can be expressed in terms of P naught upon P1, and VR can be calculated as 0.86. Now in this expression, all the value we are knowing, n is given, P naught is given, V naught we have read out, P1 is given, V1 VR we have calculated. Therefore, by substituting all the data, we have the velocity at the exit of supersaturation flow. So we had velocity. So in a similar way, from the mass continuity, by the mass conservation, we have the exit area is equal to mass flow rate into specific volume divided by velocity. So let us substitute this data, and we got an expression for the exit velocity. So in the case when we have calculated the value of exit area for the case of isentropic flow as well as when the flow was supersaturation. Now, the additional 2 points were asking that what will be the degree of supercooling and degree of supersaturation. So, degree of supercooling is corresponding to the temperature difference. That means the actual temperature difference at the exit and the saturation temperature corresponding to the exit pressure. So, let's calculate both one by one. So, if we wanted to know since the supersaturation flow follows the relation P V to the power 1.3, so in the similar fashion we can get the relationship between temperature as well as pressure. So the temperature pressure relation we will got like this one. So from this expression, the TR can be get by knowing the T naught that is given, P naught is given, P1 is knowing, N that is exponent is also given. So B will calculate it as a 383.12 Kelvin or 110.12 degrees centigrade. Also from steam table, we can have the corresponding to pressure P1, that is the exit pressure, we can have the saturation temperature. So the difference between this temperature and this temperature will give the degree of supercooling. Here we observed that the saturation temperature corresponding to the exit pressure is higher than the actual temperature at this pressure. That's why this is called as supercooling, and the difference between these two temperatures will give the degree of supercooling. Therefore, degree of supercooling we can calculate by taking the difference between these two, and that is 10.11 degree centigrade. Also, the degree of saturation, you can have the degree of saturation at the exit, the at the exit, the temperature that we got corresponding to this temperature, we can determine what is the saturation pressure. So from the steam table, using interpolation, we can get the saturation pressure corresponding to this temperature, which is at the exit of nozzle for the supersaturation flow. So the actual exit pressure and the corresponding saturation pressure at the exit temperature in the case of supersaturation flow, by taking the ratio between these two, that will give the degree of supersaturation. So in this way, we have learned here how to calculate the degree of supercooling and how to calculate the degree of supersaturation. So today we will stop our discussion here only. So thank you for listening me. Thank you very much.